models that they represent the constant 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 failure rates. So when you're trying to represent the aging devices, what you're doing is you represent it in a different stages with increasing failure rate. So that's the idea of how you can use the model to represent your problem. And her problem was, if we have the stages of device that are failing, what you want to do is you want to optimize how frequent you do the inspection at each stage, so that the inspection at each stage leads you to some kind of maintaining or improving the devices. Perhaps when you inspect and then you can go to a better stages. Like here, for example, if you're in stage 1, 2, 3, and then you go to failure, if you do inspection, there will be a chances of doing the maintenance 0.2 or 0.8. You do some minor maintenance and then major maintenance, and when you do minor maintenance, you can go back to maybe your stage at certain probability. So those are the ideas of how you use the Markov models to represent your physical systems. Now all these things that we discuss up to maybe next week, up to next week. So right now we're here, right? I started off the course by giving you some ideas of what reliability is, and then I gave you the more of the focus that reliability in my sense is not deterministic, it's probabilistic. What does it mean by probabilistic? It means that there are chances that things would fail. So we go by probability theory. From probability theory, we look at the reliability theory, which is a branch of probability theory. So they look at how you can model the time that the things would fail, right? And then when we look at the time that things would fail, we started to develop a model. We call it a stochastic process, that things have a likelihood that it will go steps to a different stages. From the idea of stochastic process, we look at how we can analyze reliability, which is very simple, right? Reliability, when we're trying to look at it, we calculate what? The probability, right? And then I told you that if the things that you are trying to look at is independent and it has only two stages, success and failure. Okay, sorry, I use up and down, right? So when the device is up and then the device is down, the device has a failure rate of lambda, the device has a repair rate of mu, then you can find the probability, right? The probability of success will be equal to lambda, lambda divided by lambda plus mu. Probability of failure will be equal to, mu, sorry. Lambda over lambda plus mu is the probability of failure, right? So, if this is the case, then when you have the devices, three devices, each device has two states. You can write the state space diagram of how many? 2 to the power of 3, right? So you have the 8 states. You have 1 down, 2 down, 3 down, and then maybe 1, 2 down, 1, 3 down, and 2 and 3 down, and then 1, 2, 3, all of them down, right? So, and the easy thing about this is that if you have the if your device is only have two states, probability of the state will be just equal to the probability of one being up times probability of two being up and three being up, right? This would apply only when this is the case, okay? And you have done that. No, we have done that in our lecture. So that is the analytical method that we have tried. We started off with the state space diagram approach, which is this state space diagram. You draw all the possibilities, right? And then I introduce you a concept of frequency. The frequency. We introduce you the concept of frequency because we say that when things fail more often. Let's see, this is your devices. The time that you fail, let's say this time is the same, right? But you fail more. You need to be able to measure that too. So we give you the concept of the frequency, right? So that's what we did last time. And with the concept of frequency, we know that frequency is equal to the probability times the rate, okay? So from that concept, what we use is that we're using this concept to try to combine, or this is quite a lot of stages here. Let's say you have all these three generating units, each with the capacity of 100. So for the first stage, you have 100 plus 100 plus 100. This would equal to 300 megawatt, for example. Instead of representing the three units generating with these big diagram, what we can do is we can try to combine that, okay? That's what we are going to do for the frequency balance technique today, okay? Last time I think we stopped at the analytical method for the tie set and cut set, right? I gave you the idea of the frequency, and then we go over the conditional probability method for the frequency. So let's just pick it up. Let's see. Any question before we start? No? Okay. So today, homework 3, everybody gave me already homework 3, okay? Good. Okay. The thing is, I'll just give you some ideas for what's to come. What we'll do here today is a frequency balance technique, which is trying to combine the states into a smaller equivalent system. Then, for some of your problem, you might see that, hey, if I do not have this kind of individual model for individual generator. For example, generator may not have this diagram. It might have the up state, and instead of the down state, they would have what we call the derated state, and then down state. What does it mean by derated state? It means that the generator cannot supply capacity at its full capacity, maybe half, because how it's running. All these things depend on your behavior, on your problem. So how are we going to represent this, or how are we going to look at the different outage model? So in here, we will give you some ideas on how you can model your physical system in a different modelings. Okay, so this is just in the outage model, and then we look at the simulation, because imagine that this example of a 3 generating units, maybe it's just for one single node of your power system. In the States, you have like 1,000 nodes. What would you do? Of course, you can combine those nodes, but then there will be like interconnection as well. So in reliability analysis, not only that you wanted to use your analytical tools to solve it. Analytical tools means that you can write equations and then you solve the problem. You know the idea, right? You write equation. This is what? 8 by 8 matrix. If you want to know exact solution, you write 8 by 8 matrix for this kind of state diagram, because it has 8 states. But for big system, you have like 1,000 by 1,000 matrix, and then you do the inversion. Is that the idea? Well, what we do is we have what it's called the simulation methods to try to solve the problem. This is basics. This is the simplified version. You have to understand this thing, and then once you're going to apply to a bigger system, there has to be other tools that we can use, and that is why we need to look at the simulation methods. After we look at the simulation methods, I will show you how it can be applied to a different areas of reliability analysis of the whole power systems. Okay, so that's just give you some heads up on what's coming next. Have I uploaded? I already uploaded all the homeworks, right? You have seen all the homeworks, and that's just a due date. I already upload the frequency balance technique on the website. Okay, so you should have that now. So now let's look at the analytical method. This is the frequency of failure and the failure rate. This is the idea of how we can calculate the frequency. So we multiply the probability by the transition rate. Okay, so when PU is the long-term fraction of time spent in success state, this is the steady state probability in the success state, and this is the failure rate. Okay, so that gives us the frequency of failure. Okay. The frequency of failure, the way that you calculate it, depends on the topology of your network. What it means by topology is that if the two component is connected, this one is connected in what? This one is series or parallel? Series. Why is it series? Because once one component is down, the system is down, right? So when we are trying to look at the frequency, you always need to ask what is the how do you measure the failure of the system, right? Let's say for this network, I think we have the example of unit 1, 2, and 3 are in parallel, right? So we have to see, in this case, what is the failure probability? What is the frequency of failure? Am I right? Okay. Very good. I got the submission from one student on the example. Remember, I still stand by my point. I'll give you 5 extra points if you work on this thing. and then you can submit it to me. I will add it to your midterm, okay? Midterm. So another chance is that you can work on this problem using the conditional probability, or you can use the pi set, or you can use the cut set to solve this problem, okay? 5 extra points. Okay, that's tempting enough. Okay, any of these methods, okay? So think about that. Now, when we look at the frequency of failure, when we look at the frequency of anything at all, what we first do is we need to draw the boundary, okay? If we talk about the frequency of failure, we need to first identify what are the failure states, okay? In this diagram, you have only 2 devices in series. So the failure states are 1 up, 2 down, 1 down, 2 up, and 1 down, 2 down. So once you draw the boundary, you will see that the system moves from success to failure via these 2 routes. You have the first that comes here from 1 to this state and come from here to here. So the frequency of failure will be equal to probability here multiplied by the rates times lambda. And the probability of 1 up and 2 up here multiplied by this lambda, okay? So the same concept applies to that question as well. So this is a frequency from state I to state J. So the frequency of failure, if you have more than 1 state, you calculate the same thing. You draw the boundary and then you add them up. That will give you the frequency, okay? So this is just a review. I'll go quickly. The frequency itself that you saw here, we first group them into only 2 groups, which is the success and the failures. But what we'll do today in terms of the frequency balance technique, we can group them into a different clusters. Like I give you an example. If these represent a generator, and the generator of being up and down has the up state, has 100 megawatts each. The first cluster would be combined generation of 300. The second cluster would be combined generation of 200. The third cluster would be the combined generation of 100. And the fourth cluster would be the combined generation of 0, okay? And the frequency concept can be applied to each of the transition between these clusters, okay? So we'll investigate more on the frequency balance technique. And this gives you the motivation why we need to look at the frequency, because probability is not enough. When we look at the probability, we'll misunderstood our system, that it behaves well while it's not really, okay? This is a state space approach. State space approach is when you write a transition rate matrix, which is what you have done in your homework problems. Okay, I think you are very familiar with it now. And as I said, in your homework problems, you can use MATLAB, you can use whatever to solve the matrix, okay? And so this is a state probability calculation. And when you write the state, the transition rate matrix, you can calculate the probability, but it's the equations that you got from the transition rate matrix, they are linearly dependent. So what you need is one extra equation that helps you, right? Which is the summation of all the probability equals to 1. This is what I meant, that you will find that this is linearly dependent, n minus 1. So you need one extra equations, which is here, okay? Frequency of failure, frequency of success, okay? Question, does frequency of failure equals to frequency of success? Actually it is the same thing. That's why we would have the frequency balance technique to help us to calculate the probability. When we have the idea of the frequency, what it gives us is the equivalent transition rate. Why is it? Because when you group these into different clusters, right? When you group them into different clusters, you can find the rates, equivalent rates, that the state changes in between these clusters. What I'm saying is that you are going to have this picture in the end. Equivalent, which gives us some kind of equivalent rates of going from a different state. Okay, so this is the motivation, what we want to do today. Now, for the example, I think we did this example using the state space approach, and then we also try to use the network reduction approach. Network reduction is how you can combine the series and parallel structures, okay? Like if you have a series network, the availability will be just the probability of being up here multiplied by probability of being up, and then the failure probability is just 1 minus that, okay? For series network, you can find the frequency of failure as well, like in the picture that we showed you earlier. So this is the system availability, and this is the frequency of failure that you can calculate. You can also find the equivalent failure rate. The same concept, we will do that to find those equivalent failure, equivalent transition rate between the clusters over there. So I'll just go quickly. This is the summarize on index in terms of reliability. By now, you should be familiarized with these names: failure rates, repair rates, mean downtime, mean uptime, probability of failure, probability of success, frequency of failure, frequency of success. Those are all interchangeably, okay? So you should be familiar with that. There was one time in particular. You see, the mean uptime is the reciprocal of the equivalent failure rate. Mean downtime is the reciprocal of the repair rate, right? There was one time in particular called mean time to the first failure. Remember that? Mean time to the first failure. It's not mean time to failure. It's different. Mean time to the first failure. Mean time to failure. We have two F's in mean time to the first failure. So what is mean time to the first failure? It's a time that you enter the failure the first time. That average time that you enter the failure the first time. It means that your system starts from the initial point, and then the average time that you take to go to the first failure. Mean time to failure, on the other hand, means that you are now living in a very long long life enough that you went to failure and then you come back to the beginning and then you go back again to the failure. So mean time to the first failure is the average time that you go to failure. And then probably you come back, repair already, and then you go to failure again. So they look at the time. Mean time to failure is actually the mean uptime, the time that you go to failure. How do you calculate the mean time to the first failure? Remember the fundamental matrix. Homework question, okay? Work on your homework problem. That gives you the idea of the mean time to the first failure. Yeah, mean first passage time. So that's a Sydney, okay? Now we look at the parallel network. So previously we have series network. Now we have parallel network. For the parallel network, we look at the probability of failure because probability of it would fail when both fails. So you calculate the probability of failure becomes the multiplication of the failure of both. Okay. In parallel network, you can also calculate the frequency of failure, frequency of success, equivalent failure rate, and equivalent repair rate. Using the same analysis, you can find the frequency of success. Why do we focus on the frequency of success? Because it's easier to calculate from the transition of failure to success. Okay, so we got the solution here. We have the equivalent repair rate, which is the summation of the equivalent of the repair rate. And then you asked me what you need to write in your cheat sheets for the exam. Now you have quite a lot. I would recommend you writing without knowing what it means because you'll be confused, okay? So try to work out from your understanding. If you understand when things are in parallel, what are the probability, what are the rates, the transitions, then you would be able to apply what you understand in it, you know, not in a confused way. If you just write down, probably if you write down this kind of table, and then you say, okay, I'm happy, I can work on the exam problem. You're probably wrong. You probably don't understand how I give homework or the exam questions. Okay, you should know my style. Okay, memorizing doesn't help that much. Okay. Now, so for the network reduction method, you can use it to solve this problem. You can calculate all these reliability indexes. Probability of failure, frequency, mean cycle time, mean uptime, and mean downtime. Okay. Next lecture, we will look at this kind of dependent failure model, and we'll see that all the analysis that we do here, network reduction, tie set, cut sets, just doesn't help. Okay. When we have this kind of dependent failure modes, or the common mode failures, what we need is we need to go back to the most basic and always accurate, which is the state space approach. Okay, that's how we can solve for the probability. Okay, we look at the conditional probability method. In the conditional probability method, we already have the ideas on how we can calculate the probability using conditional probability method, right? What you do is you divide and conquer. So you divide your problem into two disjoint sets. You calculate the probability of each of those disjoint sets, and then you combine it. That's the basic ideas. But when it comes to the frequency, you see that the frequency has 3 aspects, not just 2. Of course, the frequency comes from, given that the component is up, you have one frequency. Given that the component is down, you have one frequency. But there might be the frequency that are moved in between when that complicating component change states. Okay? So that's why you have the third transition of the frequency coming right here. Okay? So I show you how you can calculate the frequency of failure. Okay? So look at this. You calculate the frequency of the up states, and then the x being down, and then you calculate the frequency right here, which is the difference of the probability of this block multiplied by this probability and the rates, the failure rates. Equivalently, you can calculate the probability of this block and then multiply by x being down, and then multiply by the success probability between down to up. Okay. So those are the ideas. With the conditional probability, you can calculate the frequency of failure. Okay. Look at this example. You have the frequency of failure right here. Then, now what we are left off with this cut set or tie set. So, in the cut set and tie set, what we first need to do is we need to look at the system and then enumerate the minimum cut set. So for this problem, what is the minimum cut set? This is already written in the cut set already, right? So this one is your first cut set, and this is actually your second cut set, right? Because each component in the minimum cut, all of them have to fail so that it will cause the system to fail. So this is your first minimum cut set, and your second set is 2, 3, right? So that's the example. This implies that there will be a parallel connections among these components, and each minimal cut set causes system failure. Each minimal cut set causes system failure, meaning that if one fails, the whole system fails. If 2 and 3 fail, cause the whole system to fail. So that means that each of the minimum cut set has to be connected in series. So that's why you get the minimum cut set of 1 and then 2, 3 as the minimum cut set. For the probability of failure, for the minimum cut set, let's see, because this is 5 extra points, I'll just give you a chance to work on this, okay? And then send it to me, I'll grade it, then you can go back and study, okay, how it's done. I'll just give you an idea. So you can find the probability, okay, of each of the cut sets, and then you find the probability of the failure probability by look at the probability of cut set 1 and 3. Just give you some ideas. So probability of this, probability of C1 will be so and so, probability of C2 will be so and so, and then you find the probability of C1 and C2, which is the cut set of 1 and 2 and 3. This one gives you P to the 3. And then you find the probability of failure will be equal to probability of C1 plus C2 plus minus probability of C1 and C2, okay? So according to that, this formula right here, you will find the probability of the cut set. Now, let's look at the frequency of a cut set. So the frequency of the cut set is we look at the frequency of success Why? Because all the components in the cut set are connected in parallel. When things are connected in parallel, it's easier to look at the failure states because that's how you already know the probability of failure of that component in parallel. So we can find the frequency, which is equals to the probability multiplied by the equivalent repair rate. In this case, because this cut set has the equivalent repair rate will be equal to mu2 plus mu3, right? So you can calculate the frequency C1, frequency C2. Now what about the frequency of C1 and C2? This one would be the probability of C1 and C2 multiplied by the summation of all the repair rates of all the components of 1 and 2 and 3. So in this case, it's mu plus mu plus mu. Now, when we look at this, the frequency in this case, C1 and C2, luckily, there is no double count in the cut set 1 and cut set 2. Why? Because each component appears only one time in each of these minimum cut sets. Okay, that is why you can add all of them together. Now, if it's for the in this case, if you have a system that looks like this, when we find the equivalent rates, equivalent repair for the frequency of C1 and C2, the equivalent of these two sets will be just equals to mu1 plus mu2 plus mu3, okay? This is to avoid double counting because there would be, because for the equipment number 2, it appears both in the two cut sets. But when you look at the state transition diagram, in fact, it just has one transition. Can't have two transitions coming out from the same equipment. Okay. So that's why this is to avoid double count. So that's why they assign the union sign to represent that you pick just one out of each cassette. Okay, don't double count. In this example, for the cut set, you don't see that situation because both cut sets they are disjoint, so they don't have the common component in here. But I'll just go a bit quick. When it comes to, so this is the frequency of the cut set. The same concept of how you calculate the probability of failure applies to the frequency, except that when it comes to the frequency, you have the probability multiplied by the repair rates, equivalent repair rates. You just need to be careful on how you choose your repair rates. What you need to do is you look at each of the cut set. When there's a union of the cut set, make sure that you pick just one equipment from those union of the cut set. Okay. Now, please finish this, and then you get 5 extra points. Okay. Choose any of these methods. Okay. And then you have to make sure that you're correct. How did you make sure that you're correct? You already have a solution, right? We have done that last time. You already know what is the solution of this. Any of these methods you do, it must come out to be the same solution. It must be the same solution. So work on it. Either you use the cut set, tie set, or conditional probability. For the tie set, what do? Your system is 1 in a series of 2 and 3 in parallel. So what is your tie set equivalent? 1, 2, and 1, 3. Right? So what you do is you draw this picture. 1, 2, 1, 3. That's it. Right? So you have 2 tie sets. Now in these 2 tie sets, you have a common equipment, which is number 1. In the tie set method, you enumerate the minimum tie set. So the minimum tie set says that all the components in its minimal tie set will give the system failure. Give the system success. This means that it represents the series connection among these components. But each minimum tie set causes the system to success. So this implies the parallel connections among the minimum tie set. Okay, so that's how we can write the equivalent model of the tie set of this problem. Now, you can calculate the system availability. Okay, not going to repeat that. I think you should be able to do that now. But when we look at the frequency, for the frequency of the tie set, each of these are in series. So when we look at the series, for the series system, we look at the failure rates because it has just one state in the success when it comes to series, right? For the series, 1, 2. Success. So when you success, you have the rates to number 1. Okay, so you can find the equivalent failure rate to be lambda 1 plus lambda 2. Okay, so the equivalent failure rate of a tie set will be summation of all the failure rates in that tie set. Okay. Now for each tie set 1, you have 1 and 2, right? Tie set 2, you have 1 and 3. When you union T1, T2, you get 1, 2, and 3. So when you have the equivalent failure rate of this union here, it will be lambda 1 plus lambda 2 plus lambda 3. So you just pick just one, okay? So you just to avoid the double count. And that's how we can calculate the intersection. They have to use the same notation. Okay, so the frequency of the tie set intersection will be equal to the probability of this tie set multiplied by the equivalent of this set which is equal to lambda 1 plus lambda 2 plus lambda 3. So please work on this thing, okay? You have 3 methods, each of this, okay? Try to work on that. Maybe you can give it back to me with the homework number 4. Okay. So that's the frequency of the pi sets. The same concept. This is to avoid a double count. So we just pick just one from each of the sets. Okay. So those are all the reliability measures for the for the analysis. In this case, it's the same thing. So to summarize, what we did was we used the analytical methods for the reliability analysis. Okay, we have the state space approach that we can use Markov equations to calculate the probability of each state. And then we have the series and parallel network to combine the states, combine the equipments in series or in parallels. And we have the conditional probability in the case that you might have the bridge and you cannot you have the complicated component, and then you have to find a way to calculate the probability reliability here. So we can use a conditional probability to remove this component and then use a network reduction analysis to find the probability. So now from here, you can also calculate the frequency, right, for this network, for this problem as well. And then we have the cut set and tie set method. And then we use the frequency calculation to calculate all those. And next, any questions about this? Any questions? So maybe you can try to complete this and then find a solution for the cut set, tie set. So now we're here at the frequency balance technique. Maybe we have a break now, okay? For like 10-15 minutes, and then we'll come and finish this thing. I think we can finish a bit early today. Okay. You have the probability with the rate, and then that V equals to 0, right? Probability times rate equals to 0. And in a sense, the rates, the transition rates, the diagonal values of the transition rates is actually the summation of the negative values of all the transition rates. So if you rearrange that in different ways, you'll find that each of the equation tells you the frequency balance of those states, So what is the point of doing this frequency balance approach? It's actually the same thing as the state space approach, but one aspect that we get extra from the frequency balance technique is that we can calculate the equivalent transition rates. Okay, we wanted to find this equivalent transition rate. Why? I gave you the motivation right here. Okay, and when we look at how we apply these models to to power system analysis, there's one area, we call it the generation adequacy. Generation adequacy look at the, you have this generation, you have the transmission line, and then you have the load. So when you are looking at one single area, maybe Bangkok area, you might have a generation coming in, and you might have more than one generator. Okay, you might find that your transmission line is very well connected, so you're not really concerned about your interconnection, your flows, your network flows, but you're more or less wanted to know whether you have enough generations to serve the load. So when they look at this kind of problem, they wanted to know, when you combine all these generation units, how much capacity would you have at each set, and would that be able to satisfy the load? Now, there will always be the case when you have the generations of 0, okay? What you want to know is how much of this probability, okay? And what you want to know is how much of the probability of generation would be at this step, and how much of the generation will be at 200, and how much generation will be at 300. This is like going back to your first quiz. Your first quiz is actually this. Essentially, it is like this. So it is how the most simplified version of power systems, which you have a generation, you have a transmission, and then you have the load. Each of that has a different distribution, and then you try to combine everything and trying to see what is the end that the load will see. But first, you must be able to adjust or find the equivalent model that will represent your generation, right? And then you, this is the generation adequacy. And then when we look at the transmission as well, we look at the composite system. The difference between the two is that when you look at the generation adequacy, you don't care of the power flow. Okay, just look at the power flow. You say that enough capacity for the transmission. But when you look at the composite system, you say you have this generation, you look at the transmission line, probabilistic behaviors, as well as the power flow. And those things I will introduce to you. We can't really do the analysis in this class, okay? It has a lot of, you need to use those kind of computation. Just power flow, just reliability analysis, we can use the simulation methods to do the sampling and then calculate the probability of frequency. But when you combine it with the power flow, what you need to do is you need to write a program that links to the power flow analysis, and then convert it back, send back the values. Alternatively, you can simplify, and we'll look at that as well. The power flows can actually be simplified by, you have the AC, alternating current flows. You can decouple them, right? You can decouple them, and then you can have the direct current flows. If you have the direct current flows, it means that you can preserve some characteristics of the current Kirchhoff's law. All these power flow is actually this is coming from Kirchhoff's current law and Kirchhoff's voltage laws, right? And you can write all the summation of the power will be equals to 0 in comparing all the losses. So you have this power flow model, which is the AC model, and then you simplify it to the DC model, and then you can simplify it further. We call it the transportation flow. What it means is that you have something like looks the same as state transition diagram, but it's not. It's more like reliability block diagram of different nodes, giving you like you have the source right here, source, which is the generation, and then you have the network points that represent the different nodes of your system, and then you have the sink node. Okay. So in the network flow model, you only look at the capacity of the transmission line, say 200 megawatts, 100 megawatts, but you don't look at the Kirchhoff's voltage law, meaning that the congestions, how the electricity actually flows. So these are the different models. So just give you some motivation of how we would probably use this thing. Okay. So now come back to the goal of today's lecture is we wanted to write the model here, and we wanted to be able to write the equivalent, let's call it the state 300 to 200, 200 to 100, 100 to 0, okay? And the same thing goes here. You want to find the equivalent repair rate from 0 to 100, 100 to 200, and 200 to 300. So that's what we will do using the frequency balance technique. We have done quite a bit of the review, so let's just go a bit faster. So you have the idea of the mean time to failure. The mean time to failure is actually the summation of the time in the up state divided by the number of up to down state. This is what I mean by the difference of the mean time to the first failure and mean time to failure. Okay? Mean time to the first failure is the first time that the system encounters failure state. So that's a new difference. And the way that you calculate it is different. Mean time to the first failure is calculated from the first passage time through the state space diagram. Okay? Through the fundamental matrix. Okay. So you have the mean time to repair, which is the summation of the time in the downtime divided by the number of the transition. And the mean cycle time is the whole cycle from up to down. So it's just basically summarizing the mean uptime and mean downtime concept of the transition rate from state I to state J. So this is a transition from a collection of states, not just a failure to success anymore. So it can be any state. So in this case, you wanted to know the transition between state of 300 to 200 and transition from 200 back to 300. Okay, it's the same concept that can be applied. Why is it that we often talk about this? Because when you look at when we look at this kind of model, we get carried away by having seen all this, and then we see it as just the mu and lambda failure rates and repair rate. But essentially, as engineers, all these has to come from data somewhere. Okay, so when you look at these things, trying to recall that all these has the physical meaning. It means that when you go there and then you go back and work on your problem, you have to collect certain data to use that to build this kind of model, right? So when you use that, when you collect those data, recall that what it means in the physical sense, okay? The transition rate is nothing but how you observe the system through time. When you observe the system through time, what you do is you classify your system into different states, and then you observe how the system moves from one state to another state. You move back, move up, move down, whatever, and then use those information to come back and then construct the transition rate between states. That's how we build the model. You can't just build a model without the data, right? Once you build the model, you need to supply that with its parameter. Those parameters in your models come from this kind of thing. Okay, so that's why I wanted to always go back to the definition of how you observe the state up and down. Of course, these steps you can have more, right? You can have for example, when you modeling the load actually changes with time. The load is also modeled as the Markov model. So when the load changes with time, what we do is we kind of discretize it in the different steps. And then with those steps, what you do is you observe. Let's say, okay, you may have 1, 2, 3, 4, 5, 6 steps, which is the stage of your load, right? And what you do is you observe how long it takes from 1 going to 2, or maybe sometime 3 will go to 5 directly. So your transition is constructed based on this time domain, right? You might have state 1, 2, 3, 4, 5, 6, and you will go from 1 to 2, and then from 2 to 3, 3 to 4, 4 to 5, 5 to 6, or sometimes you go 1 to 3 directly, or 1 to 4, right? How often? Look at the data. Then use that to construct this model. That kind of a load model is quite common. Okay? It doesn't have to be just load. It can be whatever data that you're trying to analyze. Okay? Or it could be you're observing your transformer. You might have a transformer. Actually, that's my one of my previous Saranga, the lady from Sri Lanka. She was working on the maintenance model, and what we did was we worked with the local example, you have a Singapore Power. Singapore Power looks after the assets of the system. Assets means transmission line, transformers. So we work with them and then use that data to see the stages of devices. Okay. And then trying to see when the device moves from one stage to other, and use that to construct the Markov model. So in this case, you have a two-state exam. This is just a two-state up and down. Like I said, it can be more than that. It depends on your problem. And what you need to recall is that the time that you change state is the exponential distribution. Why? Because it's a constant rate. Okay. So if you have aging devices, your aging devices should have more states that represent the deterioration. That the more that you move on to the next stage, it means that the more that you age. Then you have the frequency. Okay, the frequency. Okay, I think you've got the idea how you can calculate the frequency, which is the multiplication of the probability and the transition rate. Okay. In this case, frequency again. The frequency talks about from state I to state J. So in this case, for us to calculate the rates from, maybe 300 to 200. From the rate 300 to 200, what it means is the frequency of going from 300 to 200 will be equals to the probability of being here at 300 multiplied by the rate. Okay. So now you have the idea. The probability here is, we know that each of the device would have just these two states. So you have the probability of being up, and you calculate the probability of being down. Okay. So from here, you can calculate the frequency. Okay. So you know the frequency of from 300 to 200. How do we do the frequency? Remember, first thing is always draw the boundary. Recommend you draw the boundary because you remind yourself how many transitions it has, count it, so you make sure that you don't miss anything. Okay, so you know that this is just a transition. So you have the probability here multiplied by the rates here, here multiplied by the rates here, here multiplied by the rates here. Okay? And that's how we can also calculate the equivalent transition rate. Okay. I can actually end the lecture here because you know the concept now. Right? Very simple. So that's the frequency balance concept. At the steady state, what it says is that the frequency of going in a state is the same as the frequency of coming out of that state. At the steady state, it should be like this. So all the frequency means that if you draw a boundary, any boundary, for example, you draw a boundary here, it means that the probability, the frequency here to here is equal to probability here times the rate here plus probability here times the rate here plus probability here times the rate here. That summation of the frequency will have to be the same as the frequency of this boundary going back. Okay. So that's what it means. So you can calculate. Alternatively, you don't want to calculate frequency here you can calculate probability here times the rate plus probability here times the rate plus probability here times the rate must be the same thing. Okay. So what does it do to the concept? It helps to calculate the state equilibrium of a system. It means that you can have an alternative way to calculate the probability. For example, you have this up and then you have this as down. Okay, and then you have the failure rates and you have the repair rates. Frequency concept. First, draw the boundary. Once you have the boundary, you find the frequency. So the frequency of going here to here is the probability up times lambda must be equal to the probability of down times mu. Okay? That's the frequency balance technique. And then, of course, you need the auxiliary equations, which is probability of up plus probability of down equals to 1. Two equations, two unknowns. Then you can solve the equation. So here you have PU will be equals to mu over lambda PD. Mu over lambda PD plus PD equals to 1. So mu plus lambda over lambda PD equals to 1, or PD equals to lambda over lambda plus mu, and PU will be equals to mu over to lambda plus mu. So that is how we can use the frequency balance technique to solve this equation. Okay, how are we going to write this transition rate matrix? Transition rate matrix, from up to down, this is lambda, right? Right? From down to up, this is mu, right? And the diagonal is the minus of it, right? It's exactly the same thing, right? The probability up, probability of down, multiplied by transition rate matrix must be equal to 0. Sorry. So we have the first equation, PU plus PD equals to 0. Second equation, PU minus PD equals to 0. Same thing. So that's why I said the two are the same. It's just a different way that you look at the equation. Okay? So for the frequency balance technique, gives you the same thing as the state space approach. But the only thing that we look at the frequency balance is that we can have this equivalent model of the equivalent failure and repair rates, because you can't have the same idea as in the state space approach. Okay. that's how I think I already explained that point for the state probability calculation. You have the same sets of equations. Okay. So you can compare that. It's the same thing. The same thing. Okay. You have n-1 equations. This is a simple equation because it has only two states. Once it has more than two states, it's a little bit tedious. I wouldn't say it can be calculated, it's just tedious. When you have more than two states, it might be better to write in the state space approach, because state space approach gives you the transition rate matrix, and with that matrix it is more systematic. Okay, so what I find is it is useful to use state space approach to calculate the probability of being found in each particular state. However, if you want to find the equivalent value, you want to combine the states. Yeah, it's better or it's easier. Actually, that's the only way to do is to through the frequency balance. You have this one state, second cluster, that we call it, and then 3. Okay, so in this case we have four states that we wanted to combine. Okay, so this is the example of a two-state component that we can calculate the frequency balance technique and use the Markov equations, which is the state space approach, to calculate the probability. Now, the frequency itself has a concept of a subset of the states as well. What it means is we can calculate, this is the frequency of being in 300, the frequency of 200. What we can do is we can have the cumulative frequency. What is cumulative frequency? Is that you can find the states. It's the same thing as the probability. You have the probability and you have cumulative probability, right? The same thing, cumulative, the frequency would be combine the two the states of greater than or equals to 200, and then here is greater than or equals to 300, and here is greater than or equals to 100. Why all the confusion? Well, sometimes you might be interested only when, if the load is 150, you only care to know when the generator is greater than or equals to a certain value of the load, right? You don't want to know you might not want to know each of these states, because you want to know the cumulative easier, right, for different loads. So for the frequency concept, the frequency of entering the subset X from any state, the definition of the frequency of entering a subset is we denote it by frequency of going into X will be equal to all the transition that comes into X, okay, that comes into X. So it can come from these states right here or whichever. So we summarize all that from the state space minus X. Sometimes we use this, okay, excluding X, state space excluding X, that comes in here. Basically what this equation is saying is that we don't look at the transition within the states. We only look at the boundary of this subset. Okay. So with the frequency balance technique, it means that what comes in must be the same as going out in terms of frequency. So the frequency can also be applied to a set of states. A set of states, which is here. So we can combine the states, okay, as a subset. If these are the state space, each of these are the subset of the state space, they are disjoint. So we can find the frequency from a subset, meaning that, let's say, we wanted to know the frequency of generator from 100 changing to 200. And that is this frequency right here. Because 100 capacity, you have 3 states representing that. 200 capacity, you have 3 states representing that. So these between the subsets, frequency can take care of that too. So this is a frequency, not just one state to the other, but a subset of states. Subset means that you combine different states into one. Okay, so that's why you have this concept. So in the set frequency, you can calculate the example here. You have 2 states. You wanted to find the frequency of producing 100. Okay, the frequency of producing 100 means that you calculate, you first again, every time you do the frequency, draw the boundary. Okay, once you draw the boundary, what is the boundary? You want to know producing 100. You draw the boundary of where you see the states producing 100. Okay, in this case, 2 units example, each unit of 100. So this is your state with 100, and this is another state with 100, right? So you draw the boundary. So you see that the frequency of going out, producing 100 is probability here times here plus probability here times here, and then the probability here times this transition, and probability here times this transition. And that's how you can find the set frequency of producing 100. There's another concept of the frequency of producing greater than or equals to 100. Okay. When you want to find the frequency of producing greater than or equals to 100, again, draw the boundary. Where is it greater than or equals to 100? Here. This is 100 or above. So you have the boundary right here. So the frequency of producing greater than or equals to 100 is the probability here times the rate plus the probability here times the rate. Okay. This concept of the frequency, we will see it again in the generation adequacy, and in that we call it the unit addition algorithm. The unit addition algorithm is the calculation where you can start adding 1 unit at a time. You see that you have if you have 1 unit, your calculation is quite simple, right? For the probability. If you have 1 more unit, you add just 1 more unit. You can have the algorithm that can take care of that in each of the steps, like adding 1 more unit at a time. So we'll look at that later on in generation. concept, everything is coming from here, from the frequency balance technique. Okay, so the frequency has the purpose of helping us to reduce the state transition diagram. State transition diagram here states with same characteristic. What are the characteristics? It produced 100, it produced 200, and it produced 100 right here. So we want to combine that. And you see, for the probability, we already know that if we want to find the probability, it's very easy, right? Probability of this state is just the probability here plus here plus here, right? The probability that you will be found producing 200. The probability that you will be found producing 100 will be probability here plus here plus here. The only thing is that, what about the frequency? So we use the concept of the frequency balance to find it. So the concept of the frequency balance is that you have the frequency here, the frequency from 300 to 200 will be equals to the probability of 300 multiplied by the rates of 300 to 200. But you know that the frequency here is actually equal to its own probability P of 300 multiplied by what? This is let's say lambda 1, this is lambda 2, and lambda 3, right? So this is actually the probability here times this lambda 1 plus probability of 300 multiplied by lambda 2 plus probability of 300 times lambda 3. Right? So in a sense, you will see that the equivalent transition is actually here. Okay? So what you do is you can represent the picture, the transition diagram here with this, with the lambda 300 to 200 will be equal to lambda 1 plus lambda 2 plus lambda 3. Okay. Very easy. So this is the equivalent transition rate for the two component each with 100 megawatts. So we can reduce this into from 4-state diagram to 3-state diagram with 0 capacity, 100 and 200 capacity. So maybe we just look at the example here, and then you can try to work on a 3-state, three generators. Okay. So in this example, okay, I have 4 identical units. Maybe we'll work on this example first of the two units. So from the 2 I think we simplify that all of the transition rates are the same. I mean, for the two cases. So first, you have the frequency. Okay, in this case, draw the boundary. This is 200, and this is 100, and this is 0 megawatts. So what you want to find is the equivalent 200, 100, and then 0. So first, we already found this thing, lambda 200 to 100 will be equal to the frequency, right? The frequency is the probability here multiplied by this lambda plus here multiplied by this lambda. So you get probability of 200 divided by lambda, multiplied by lambda. Plus probability of 200 multiplied by lambda. But we know that the frequency here will be equal to probability of 200 multiplied by lambda of 200 to 100. Okay. So this means that lambda 200 to 100 will be equal to lambda plus lambda. So this is 2 lambda. Okay. What about the frequency? What about this probability here? So in this case, frequency of 100 to 200. Okay, so this frequency, the frequency of going from 100 to 200 will be equal to the probability of write it down. Call it 1, 2, 3, and then 4. Okay, just to name the states, otherwise it will be quite confusing. So from the frequency of 100 to 200, from 100 to 200, this is the probability 3 multiplied by mu plus probability of 2 multiplied by mu. Okay, the frequency of 100 to 200 will be equal to probability of 100, right? Multiplied by the equivalent repair rate from 100 to 200. Okay, which is equal to P3 plus P2 mu. But then P100 is actually equals to P2 plus P3. So this means that equivalent repair rate from 100 to 200 will be equals to mu. This is mu. Okay. Okay. Now, what about these two rates? Frequency. Can I erase this? Yeah. Yes. No. Okay. 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 Maybe I'll write it here. The frequency from 100 to 0, from 100 to 0, will be equal to the probability of 2 times lambda plus probability of 3 times lambda, right? And the frequency of 100 to 0 will be multiplied by the rates of 100 to 0. But again, this probability of 100 is actually P2 plus P3. So this means that equivalent lambda will be equals to just lambda, right? Okay. Last thing is the frequency of 0 to 100, which is equal to P4 of P0 itself multiplied by the equivalent repair rate of 0 to 100. And that equals to P4 multiplied by mu plus P4 multiplied by mu. And that's equals to 2 mu P4. But P4 is actually P0, so equivalent repair from 0 to 100 will be equal to 2 mu. Okay? So that's how we can calculate the equivalent repair rate and the failure rates of these units. You see there's a pattern here. Exactly the same pattern. You can apply that to a three-stage unit. And in this example here that I've given in the slides is actually the 4-stage units. Okay? So you have 4 states. Each of these have identical 50 units with a failure rates of lambda and mu. What we want is the equivalent steady state model to describe all possible capacity states that 4 units generate, along with the probability as well as the equivalent transition rate. So what it means is that what I want to see is what is this equivalent model, right? For 4 units, you have 2 to the 4, which is 16 states. So you can have this state space diagram. Normally in the analysis, at least in the US or in the US and Canada, where they have multiple generating units, each node might have tens of the units that attach to it. I know that the analysis will be different from different regions. Okay, so in the case of Thailand, I'm not quite sure how many units there would be. Probably not that many. But in any case, this is the way that we can propose the equivalent model. As you can see, just 4 units, you can have quite a mess state transition diagram, like a 16 states. But if you combine it, you have left with only 5 states, which are the same analysis, the same equivalent. So what we first need is, first we want to know what are the probability of being 200, 150, 150, and 0. And that probability, again, if you have identical units, each unit has only 2 states, being up or down, you can easily calculate the probability, okay, of here, of each of these. Probability of being in this state will be equal to probability of 1 up times 2 up times 3 up and times 4, right? So you can easily find the state probability of each of these states. Then when you combine it, you can calculate the probability here. So for 200, you only have 1 state, which is state 1. For 150, you have 4 states, which are 2, 3, 4, and 5. For 100, you have 6 states, okay? And for 50, you have 4 states. And for 0 you have 1 state. Okay. So as you can see that, you could almost see some pattern already from the calculation here, that you have 4 states. The very first rates, failure rates, it's like adding the 4 units together, so you have 4 lambda. From 150 to 100, you have 3 units failure, so 3 lambdas. From 100 to 50, you have 2 failures, you have 2 lambda. And then from 50 to 0, sorry, I think that's wrong. So it has to be 0. This is supposed to be 0, okay? So you have 1 lambda. Okay? So that's how you find the equivalent transition rates. And for the repair rate as well, from going from 0 to 50, you have like almost 4 units, 4, you can see that, 4 transitions. So you have 4 mu, okay? And here, you have 3 from 50 to 100. And then from 100 to 150, you have 2 mu. And from 150 to 200, you have 1. Okay, so it's almost like a pattern. And those kind of pattern is what they would use it for the unit addition algorithm. So that we don't need to write out the whole state transition diagram every time we have 1 more unit adding into the service. The unit addition algorithm is useful in a way that when you have existing equivalent model like this, you want to add 1 more unit in your network. So you need to, it's almost like you have 1 more, it's like you're adding 1 more unit, and you don't want to recalculate all these tables that you already have. So in the unit addition algorithm is the idea of how you can add just 1 unit and append your model to become bigger and bigger, right? Because we first start with 0 and 100. This is just 1 unit, and you have 1 more unit. You have 200, right? And you have 1 more unit. You have 300. So that's the idea of the unit addition algorithm. We'll go quickly, okay, with those things later on. So I guess that's all for the analytical methods. I think we have covered every possible solutions to calculate 2 index. See, we're not moving anywhere from probability and frequency. So those are the 2 units of reliability analysis that we will we have and we study. When we move on to the thing is, when we talk about the probability, people get confused, right? As engineers, when you talk to users, you talk about, oh, my system has 99.9% success, and they will say, oh, what are you talking about? So sometimes it's better to change those probability into something that they would it will be easier to understand. For example, you might say that our system will experience loss of load only 2 hours in 1 year. You see, those 2 hours in 1 year, those are actually just the probability, right? But it's in the other way that we use to communicate. We don't talk about probability, but we talk about the expected time. Okay, so it's basically it's a probability times the time, the hours, number of hours in 1 year. And once we get into the power systems, another aspect is that how much of the loss of load, not just the time, but the magnitude of loss of load. So those magnitude of loss of load, sometimes you need the power flows to help you calculate. Because what you have here is just the states and probability. But what you need to know is that with these states, how much of the capacity is transferred to your customers, and does it match your customers, right? So those you need power flow to help with the calculation. Okay, I think that is pretty much what we have done. This is the reading materials. You can take a look at that. So next lecture, what we will do is you don't normally have just only two states. The two states is to explain it in an easier, simplified version. You also have other available models. So we'll give you example of other outage models and how we can calculate the reliability index and how can those models can be approximate to our usual two-state model. Okay, so we'll do that next week. Any questions?